Oh, okay. Yes, you literally do have to hit it twice. Okay. Um, all right. Hello, everyone. My name is Patrick DeBonis, they, them. I just finished my PhD at Purdue. Rolando is one of my advisors. Um, so I will be talking today about the Borel functional calculus. And you can, I'm going to have to write kind of big, so you can follow along on the note and the links I sent. I don't know how real time that'll be, but that'll let you scroll back. Okay, so, right. So yesterday you learned about the continuous functional calculus. And so this is a generalization to it that works better for von Neumann algebras. Um, so I'm just going to recall the continuous functional calculus. So first, we want to let x be a normal operator. Uh, just recall that means x adjoint equals x adjoint x equals the identity. And then remember that you look at the norm closure of all of the polynomials and x star and the identity. So I don't know, norm closure. So this is an abelian C-star algebra. And we write it as C-star of that operator X. And you use the Gelfand transform going from C-star.
Hey Patrick, I think you have the definition of a unitary, not necessarily normal.
Oh, that's true. What am I missing for it to be normal?
You just don't need equals identity.
Oh, okay. Okay, yeah, yeah. Thank you. Yeah. In particular, self-adjoints are normal. That's usually what we do here. Um, yeah, if anyone has questions or concerns with what I'm saying, hopping off mute is the best way to get my attention. Okay. So we're looking at the Gelfand transform from the C-star algebra generated by this element to the continuous functions on the spectrum of that element. Um, and right, this is a isometric isomorphism, and it goes. You have a continuous function um, on in the spec right. The spectrum of this operator is a compact space, and you have the continuous function there, and then in you're defining an operator over here, f of x, which is the inverse of this Gelfand transform, and recall that it has the star algebra structure. So addition uh, goes through with this isometric isomorphism. Composition of functions, right, is our multiplication. And then the norm of this operator is given by the norm of the infinity norm of the function on the spectrum. Um, right. So this is the star algebra structure. And we call this the continuous functional calculus. And so, right, the goal is to uh, extend this to the Borel functional calculus. And so maybe, right, kind of the idea here is that you have the continuous functions on a compact space here, the spectrum of our element. Well, that sits inside the bounded Borel functions, kind of overload B here. So when it's not a Hilbert space, I'm talking about bounded Borel functions as opposed to the bounded operators on a Hilbert space. Um, and then over here, right, are the C star algebra generated by your operator. Well, that sits inside the von Neumann algebra that's generated by the operator and its adjoint. And so, right, right, you look at the polynomials in X and X star and in one, and then if you take its double commutant, that is what we define to be the W star algebra, the von Neumann algebra of that element. And right, just remember that this is norm closure for the C star algebra, and so that implies the SOT and WOT closure over here. So it really is an inclusion here. Um, and so, right, the goal is we want to extend what we did for the continuous functional calculus to the Borel functional. Um, and then at the end of towards the end of the talk, we'll do an application of this as well. And right, sort of the idea is we want to use Borel measures to extend this to the Borel functional calculus. And I guess we'll start with the first proposition towards that direction. So just use the same numbers as in the goals notes. Uh, so let X and the bounded operators on a Hilbert space be normal. Then for any vectors, C and eta in our Hilbert space, there exists a unique regular Borel measure that we index by these vectors. And it's inside, right, the space of all measures on our compact space, the spectrum of this element, which is itself a vector space or a Banach algebra even, satisfying this measure. The norm of this measure is bounded by norm of these vectors. And for a continuous function, if you, well, yeah, for a continuous function applied to your operator, so in the continuous functions on, let me just write this down and I'll say the words. So if we start on the right-hand side, what you have is a continuous function on the spectrum of your operator. And so integrating against this measure here is the same as taking an inner product against the operator f of x. And so label this equation. And it also needs to satisfy some of these star algebra properties. So conjugation of this measure switches the order of those vectors. And then it's going to be this idea of linear in the first component. So here, alpha is a complex number. And then conjugate linear in the second component. Now beta is our complex number. Okay, so this is the proposition. Um, and so let's go ahead and prove it. See, this is why I shared the link, because I cannot fit very much on my screen at once. Okay. Um, proof. Okay, so first we can show that this is a bounded linear functional. So for f, um, continuous function on the spectrum, uh, then this inner product, the way it's is going to be bounded. Um, right, pulling out this operator f of x and then using that what we know that that's just the norm of the continuous function, the infinity norm. And so, right, this is shows us that the map from the continuous function to this inner product um, is a bounded linear functional. Um, on continuous functions of the spectrum of this element. And so, because it's a bounded linear functional, we get to use the Riesz representation theorem. Um, and right, it's the Riesz representation theorem. There's so many versions of it. We'll actually use multiple versions of it today, but this is the one in the goals notes. Um, right, it's going to imply that there exists the measure indexed by these vectors inside the space of measures for this compact space, satisfying the property that we wanted. It's bounded by the norm of these two vectors. And then also, right, the other property we wanted, I'll scroll back up, this property star, I'll use circle it or something, right, that the inner product equals integrating against this measure over that spectrum, right? And so this is really, yeah, it's just coming from the Riesz representation theorem. Um, and then, right, part of that theorem is that the space of measures is actually um, the dual of the continuous functions on your compact space. Um, and then that property is going to imply that this measure is uniquely determined by star. Right. Which again is the equation up here, that the inner product comes from integration. And the other properties, right? So other properties, which was these ones here, the conjugation and linearity and conjugate linearity in the second coordinate. Other properties are going to uh, follow from right the uniqueness of the measure, and right the analogous properties for an inner product. right? So that's worth checking at some point in the future. Um, and so basically, what we have from this proposition is that Riesz representation tells us that for the continuous functions, we always have these Borel measures for any two vectors that integrating a continuous function against that measure is the same as the inner product of the operator f of x against those vectors. And so, right, so far I'm only talking about continuous functions. So we're going to need to extend this to Borel. And just some observations now to like motivate our next steps. Um, right. We want to think about so bounded Borel functions on a locally compact Hausdorff space. So bounded Borel functions on a locally compact Hausdorff space X. Right, so these are functions from X to C, and right, this is the infinity norm. Uh, and so, right, the observation we want is that, well, for any f in this space, uh, it is integrable with respect to any measure, regular Borel measure in Fourier space. And the other observation we want is that uh, for any Borel measurable set, S and X, we have that the characteristic function of that set is itself a bounded Borel function. And for any measure, uh, we have that the measure of this set is exactly integrating against that characteristic function with respect to the measure. Right. So these are some observations just about bounded Borel functions in general for any locally compact Hausdorff space. And what, with these sorts of things in mind, that we want any definition of what this operator f of x inside now the bounded operators on h for a Borel function we want it to satisfy basically the proposition we did earlier. We want the operator, taking the operator inner product against the two vectors should be the same as integrating against that measure. And again, the proposition we did previously only shows this for continuous functions. And so that's what we're working towards, is extending this to Borel functions. And I think the thing to note is that, right, the right-hand side already makes sense, right? So RHS makes sense. And that's basically what we were saying above, is that, right, you have a Borel bounded Borel measurable function, and you have a Borel measure for that same space, then you're allowed to integrate against that measure. So that's fine. And so it's just making sense of that other side. The left-hand side is sort of the goal now, to get the Borel functional calculus. So Uh, right, need to. Okay. And so to do that, we need another lemma. So, so suppose we have Q, um, and so this is going to be a bounded sesquilinear form, but I'm going to tell you what that is. So it should be, so suppose Q is linear in the first coordinate, and conjugate linear in the second. And there exists a constant C positive, such that this form is bounded by C and the norm of your two vectors. Just hold for all vectors in your Hilbert space. Um, so suppose you have a Q satisfying these conditions, uh, then there exists a unique operator satisfying well, it should be this form, the sesquilinear form, Q of their two vectors is going to be actually realized by an inner product of some unique operator against those vectors for all vectors. Right, that's the first property, or well, and it should be bounded by this constant. Um, and right, this kind of statement should look familiar, and it is, lo and behold, another form of the Riesz representation theorem. And so, uh, right, the proof of this one is going to be an exercise in the notes, but it's actually called um, Riesz representation for bounded sesquilinear forms, and it like proving it is fairly similar to like a more standard version of the Riesz representation that maybe you've seen before. Right. The point being that if you start with this form, you know that there exists a unique operator that realizes this form through an inner product. And so the idea now is we want to put this together with our previous observation that integrating against Borel functions always makes sense. And so we want to put this together, and we can actually do prove the Borel functional calculus now. I guess I haven't really paused yet. Well, we can do like more in-depth questions at the end when I turn the recorder off. But does anyone have any questions so far? Cool. Again, feel free to stop me and come off mute at any time if you do have questions. And if you want to scroll back up to what I'm writing, the link should hopefully work. Okay. Um, so we have theorem 2.1.3. This is the Borel functional calculus. So we start with a normal operator the bounded operators in the Hilbert space. Um, so there exists a star homomorphism from the bounded Borel functions on the spectrum of that operator to an operator which is Borel function of this operator, and it will be exactly inside the von Neumann algebra generated by that operator X. Okay, so let's prove it. So we want to start first. Let's fix a bounded Borel function on the spectrum. And so for any vectors in our Hilbert space, we want to define something that we will sort of suggestively call Q, like in the last proposition. Define this function to be, well, the thing we know about already, which is integrating a continuous function against a measure. Integrating a Borel function against the measure. That's the whole point. That's what we know that about the Borel functions. And so this measure is exactly the one is from the first proposition we did. Right? And that one, it was used for continuous functions, but we also know that it still makes sense to integrate this for Borel functions. And so now what we want to do is argue that this Q is actually a bounded sesquilinear form, and so that we can use this previous lemma up here. So that's sort of what we want to argue now. And we basically use the properties from this first proposition. And so, let's see, prop 2.1.1 is going to imply that Q is linear in the first coordinate. And conjugate linear in the second. And also that it satisfies, sort of by definition of how we're defining it in terms of this integral. It's bounded by integrating the absolute value of this function against the absolute value of this measure, which in turn is bounded by the affinity norm of this function, the norm of this measure. And remember from the first proposition 2.1.1, we know that this measure is then bounded by the norm of the two vectors. And so that tells us that, so we conclude that Q is a bounded sesquilinear form. And so we can use the lemma above. So lemma 2.1.2 implies there exists some operator, we're calling it Y for now, bounded operators on the Hilbert space, such that well, it's bounded by this f infinity of the function, right? That's our constant right now. And it satisfies the inner product property, right? This sesquilinear form is being bounded sesquilinear form is being realized by the inner product against this unique operator y. Which, right, of course, we defined it to be the integration against this measure. This is for all vectors. Um, and so, right, we know that such an operator exists by this previous um, lemma, which is another version of Riesz representation. And we're actually just going to now define what the Borel function on this operator, x is going to be defined to be this unique operator y. And because Q is this bounded sesquilinear form, this means that the map from the bounded Borel functions on the spectrum to this operator f of x is contractive. And then the point here is and hence continuous. Uh, and right. So then the next thing we want to do is show that it is satisfying the star algebra properties on the operator side of things. And so then we can check that for addition. So for all vectors, we have that, right, addition on the operator side of things, which is doing in the inner product. That becomes integration of these Borel functions on the spectrum against this measure. And so then, right now, just using properties of integration, split this. And right, that is just now back the inner product against these. And so then this shows us that the addition structure on the operator side of things is going through. And it's really going to be, right, so, right, this implies that the operator f plus g of x is the same as addition of these two operators. And you really use this same process to show that the multiplication goes through as well. And then the adjoint as well. So, right, these two. And so what that tells us is that this map, right, from the function to the operator is a contractive star homomorphism. And at this point, it's worth noting, so a note that right, by construction, for the function, the continuous function on the spectrum, then the operator, um, right, it agrees with what we did yesterday for the continuous functional calculus. Okay, so we have that this is a contractive star homomorphism, but right now, all we know is that this operator f of x is just inside b of h. And so the next thing we need to do is, right, so now we need to show that f of x is actually inside, right, this w star, the w star algebra generated by that operator. And to do this, we're going to, right, really take advantage of the being able to understand this is the double commutant of the polynomials in x and x star. And so let us do that. So, right, the first thing is that we want to actually um, show something about the measures we're using and their vector, right? The measures we're using in this star homomorphism we've constructed. And so to do that, we need to start with, well, let's say we'll start writing things and say it maybe a little bit more concretely. Um, so we want to observe that for an operator and the commutant of these polynomials, um, and a function that's continuous, right, in vectors, or Hilbert space, uh, we want, right, because we are working with a continuous function right now, we can just see that that if you look at y f of x minus f of x y inside the inner product, well, this is just zero. We know that because, right, it's an abelian, right? These functions commute with each other. But the point is that when we pull this through and write it as the integration, I guess first we take y over with its adjoint. This is now integration f. And actually, right now we want to pay attention to what these measures are right now. So this first one, it's xc and then y star eta minus integrating against y eta, or sorry, y xc eta. And right, the point is that since we started with an arbitrary continuous function on the spectrum, and both of these measures, see y star eta, right, both of those are the measures on space of regular Borel measures on this the spectrum of our element, and that is the right, dual of the continuous functions there. This is going to imply that the two measures are equal to each other. Right? That's a property that you'd hope is true, but we did need to check it on the continuous functions because that is where they're defined, and then we extended this to the Borel functions. And the point is that um, because you can integrate any Borel function against any of these measures, and by what we've shown above so far, we have this contractive star homomorphism, then to understand what happens in the inner product for a more general Borel function, right? Uh, so more general Borel function now on the spectrum. Uh, Now that we know that these two measures are equal to each other, we have that seen if these two operators commute for a more general Borel function, we can make sense of that as the integration, since we know these two measures are equal to each other now. We get that in the inner product, this is zero, and this is for all y in the commutants of these polynomials and x star, and 1, and all vectors. And so it follows that we really do have commutation of these two operators for all y, right? I guess I already wrote that. And so since f of x is commuting with everything in the commutant, so then what that tells us is that f of x is in the double commutant of these polynomials. And that's right exactly the von Neumann algebra generated by our operator. And so that actually concludes the proof of the Borel functional calculus. And so really like the whole idea of trying to show that this f of x is in the right place, we basically had to prove that these two measures were equal to each other for continuous functions, and then use the contractive star homomorphism we defined above, to get that f of x is in the double commutants. So yeah, any questions that of the Borel functional calculus? We're going to do an application of it, but I figured this is a good point to ask. Okay, cool. Um, and right, so keep going. Okay, so I guess maybe sort of the first idea that we're going to use, really the main idea for this application, is that characteristic functions uh, functions are projections. So what does that mean? Um, so if you start with uh, a normal operator again, B of H, and a Borel measurable set inside its spectrum, then the characteristic function, right, that is definitely a bounded Borel function on the spectrum. Um, and we can observe that it's equal to its own conjugate and its own square. Right? Squaring a characteristic function doesn't do anything to it. And this implies, right, through the Borel functional calculus that we just proved, that the operator corresponding to the characteristic function then satisfies the properties necessary to be a projection. And moreover, uh, if you start with a bounded Borel function that is simple, so just a linear combination of characteristic functions, uh, then that means the operator f of x is a linear combination of projections. And so with this correspondence that we're observing here, we can give this application, this corollary. Corollary 2.1.4. So a von Neumann algebra is the norm closure of the span of its projections. Right, so we're saying that the projections are dense inside of von Neumann algebra. Um, and so let's see why that's the case. Uh, so start with a von Neumann algebra. Assign the bounded operators on a Hilbert space. And then we take x. Well, actually, you just start with any x, but what we can do is, and this is a trick that you use a lot in von Neumann algebras. So we just assume that x is self-adjoint. And the reason we can do this is because you can decompose an operator into its real and imaginary parts, and those are both going to be self-adjoint. It's a very nice trick that gets used all the time for von Neumann algebras, that you just prove something for self-adjoint operators, and then it's going to hold for all by extending linearly to its real and imaginary part. So these are both self-adjoint. Um, so in particular, x is normal, and by the Borel functional calculus, f of x is going to be inside the von Neumann algebra generated by x, which sits inside M for all bounded Borel functions. And right by the previous discussion, previous observations, up here where we saw um, that the characteristic functions correspond to projections, and a simple function is a linear means that f of x is a linear combination of projections. Um, we can uh, approximating, so by previous observations, approximating the identity function on spectrum of the operator uniformly by simple functions, then gives an approximation of the operator by a linear combo of projections in M. Right. Again, this is by the Borel functional calculus. Right. And so what this says is that since any operator in your von Neumann algebra can be approximated by uniformly by simple functions and a linear combination of projections, that tells us that the projections are dense inside your von Neumann algebra, which is very, very nice. Lets us use projections to prove things about von Neumann algebras a lot. And it's also, right, it should be contrasted with C star algebras, uh, which are more general and do not have to have this property. Um, with C star algebras. Um, and then there's lots of C star algebras with no non-trivial projections. Right. Just look at the continuous functions on a compact Hausdorff space. Then the only projections are 0 and 1. I believe there's a link to a non-commutative example in the notes as well.
This is if the space is connected, right?
Yes. Yeah. Yeah. And so I guess maybe I don't know if this comment will mean, well, I guess I get to say the comments at this point, right? That maybe I'm a lecture ahead, but this is where you get the version of people say that, right, studying C star algebras is the non-commutative topology and operator algebras is non-commutative measure theory. I guess you have to wait till the next week for the abelian von Neumann algebra lecture to really get that comment to be solidified. But yeah, I'll go ahead and stop there and open the floor for questions that, oh wait, no, I want to share, but I want to stop recording. Uh,